Now, we will be presenting our topic on application of first-order differential equation, focusing on two main areas which are growth and decay problem and mixture problem. These two applications are commonly used in real-life situation and help us understand how quantities change over time. In the next few slides, we will briefly introduce these two concepts and the mathematical model behind them. In this assignment, we explore two important applications of first-order differential equation, namely growth and decay and mixture problem. Growth and decay problem involve situations where quantities increase or decrease over time at a certain rate. Common examples include population growth, bacterial growth, and radioactive decay. On the other hand, mixture problem focus on combining two or more substances with different concentration to form a final solution. These problems are widely applied in fields such as chemistry, medicine, food preparation, and industrial process. Both applications help us model real-world problems mathematically and predict outcome accurately. Now, let's look at the differential equation used for this application. For growth and decay, the basic model is dP over dt equal to Kp, where P represents the quantity and K is a constant that determines whether the quantity is growing or decaying. For mixture problem, the equation is dA over dt equal to input rate of salt minus output rate of salt, or simply R in minus R out. The equation helps us track how the amount of substance in a mixture changes over time based on what enters and leaves the system.
Next, we go through the problem statement. The rate of growth of a population in a small town is proportional to the population present at any time. If there are 5,500 members after 5 years and 7,540 members after 10 years, what is the population of the town after 20 years? Now, let's move to the problem solving. We start with the differential equation dP over dt equal to Kp, which represents population growth. We separate the variables and integrate both sides to obtain ln P equal to Kt plus C. By rewriting this equation, we get the exponential model P is equal to C exponent Kt. Next, we substitute the given population values. When T is equal to 5, the population is 5,500, and when T is equal to 10, the population is 7,540. Using these two equations, we divide them to eliminate the constant C and solve for K. This gives K equal to 0.063. After finding K, we substitute it back to calculate the constant C. Finally, we use the model to estimate the population at T is equal to 20, which gives approximately 40,150.
Next, this slide presents a mixture problem involving a brine solution. This question is considered as question 2. A tank initially contains 300 gallons of brine with 300 pounds of salt dissolved in it. A brine solution with a concentration of 4 pounds per gallon flows into the tank at a rate of 3 gallons per minute. At the same time, the well-stirred mixture flows out of the tank at a rate of 4 gallons per minute. The objective of this problem is to find an equation that represents the amount of salt in the tank at time t.
For this mixture problems question, the requirement is we have to find the equation for the amount of salt in the tank at time t. So we know that AT is amount of salt in the tank at time t. The first step is we have to find rate of salt coming in, RIN, using the formula concentration multiplied with rate. Based on the question, the brine solution come in with a concentration of 4 pounds per gallon and the rate is 3 gallons per minute. So RIN is 4 times 3, which equal to 12 pounds per minute. Next, we have to find the rate of salt coming out, R out, using the same formula, but the concentration should be right as AT over volume plus minus with difference between rate in and rate out. So concentration is A over 300 minus T. We get minus T or negative T because of 3 gallon per minute minus 4 gallon per minute, which we get negative 1, and then multiply with 4 gallons per minute. So R out equal to 4A over 300 minus T. Next, we will find dA over dt using formula RIN minus R out, and we will get 12 minus 4A over 300 minus T. Then arrange to standard form, so it becomes dA over dt plus 4 over 300 minus dA equal to 12. After that, we will apply integrating factor method, exponent of integrate pt dt, where pt is 4 over 300 minus t, and we will get 300 minus t to the power of negative 4. Then we will multiply the whole standard form equation with 300 minus t to the power of negative 4. And by solving the equation and applying substitution method, we will get the actual equation, which is AT equal to 4 300 minus t plus C 300 minus t to the power of negative 4. After that, we will find C using the given statement, where at t equal to 0, A is equal to 300. So, by substituting t equal to 0 in the AT equation, we will get C equal to 900 over 300 to the power of 4. And after replacing the value C into the equation, we will get the final equation, which is AT equal to 4 300 minus t minus 900 300 minus t over 300 to the power of negative 4.
In conclusion, throughout growth and decay problems, we can see how quantities such as population increase or decrease over time. These problems help us predict future outcomes and understand how systems behave as the time progresses. Mixture problems demonstrate how systems work when substance flow into and out of system. From this, we can track how the concentration change and clearly observe the effects of inflow and outflow over time. Overall, the application of first-order differential equation help us understand real-world process. This application shows that mathematics is not just about numbers, but explaining and understanding the world around us.